Okay, so in this video we're going to be going over the practice test for projectile motion. So the first question is addressing a cannonball that's fired and follows a parabolic path, and we're considering air resistance to be negligible. Okay, so that's going to be important. Point B is the highest point, and points A and C are at the same height. In other words, that this is the same height. So we know for any projectile problem that the horizontal velocity is going to stay the same exact magnitude throughout with zero air resistance. And we know the vertical velocity on the way up is going to get smaller, so it's going from some value that's right here to 0 at point B and to the same magnitude at point C as it was at point A, just in the opposite direction. So the overall velocity vector for point C will be the same as the overall magnitude of the velocity at point A, and B is going to be the smallest. So we know that B is going to be the smallest. Okay, so we have B being the smallest here and here. Okay, so we can eliminate A and B, and that A and C are going to be equal. So we have choice D. Which of the following best describes the direction of the acceleration at point C? This whole entire time, this object is in free fall. And so what that means there is that there's only an acceleration due to gravity, and it's in the downward direction. And its magnitude is 9.8. And so it's accelerating in the downward direction this entire time at 9.8 meters per second squared. So it doesn't matter whether this asked about point C, point A, or point B, all of the answers would all boil down to in the downward direction. Number 3, we have an object thrown off a cliff with an initial upward velocity, so vertical velocity of 6, and initial horizontal of 15 meters per second. And we're told that it takes 3 seconds for it to reach the ground. So that 3 seconds translates into the horizontal, and it also translates into the vertical. And if we neglect air resistance, we're trying to find the height of the cliff. So we're trying to figure out the delta y. And so the delta y is equal to v naught t plus 1/2 at squared. So if we carefully plug that in, we have initial upward velocity, so positive 6 for the upward part, times 3, plus 1/2 times negative 9.8 times 3 squared. And if you go through and put that into your calculator, you should get the correct answer of B, which is 27 meters. Now we have an object that's thrown horizontally off a cliff. So that's the difference between something fired up at an angle, like it was in number 3, to just completely horizontal in number 4. And it has an initial velocity of 15 meters per second. So we want to know the distance from the base of the cliff where the object lands. Okay, so this is actually going to be 2 steps. We need to first figure out how long it takes to fall. So we can use delta y equals v naught t plus 1/2 at squared, where the initial velocity in the vertical is 0. Do a little algebra, you should get the time is equal to the square root of 2 delta y over g. And so in this case it is 2 times 125 over 9.8. And this is actually negative 125 and a negative 9.8. And then when you figure out that number, then you can use that in the horizontal and figure out the range. It's the initial velocity in the horizontal times the time. And if you plug those 2 numbers into your calculator, find the time. So 2 times 125, 250. 250 divided by approximately 10 is 25. Radical 25 is going to be pretty close. Well, it's going to be pretty close to 5. And then 5 times 15, you're going to get something very, very close to 75 meters. Choice B. Number 5, we have a cannon fired a projectile with an initial speed v at an angle theta above the ground. What time does the projectile hit the ground? So we are assuming some things, that it is going to be fired and lands at the same height. Okay, so that's going to be important here. So we want to know what time does the projectile hit the ground. So if we're given a speed v and a angle theta, okay, what we can do is we can say, well, we know that the initial velocity in the vertical and the initial velocity in the final, or the final velocity in the vertical, so v final in the y, those two values, like this value right here, let me do this in a different color, this value right here and this value right here are going to be same magnitude but opposite in direction. So what I can actually do is I could say v is equal to v naught plus at. I can rearrange this so I have v minus v naught divided by a is equal to t. But there's a catch here, and we got to be careful about this. The v final, I'm going to call this to be negative. So this is negative v times sine of theta, and I'm going to subtract a positive v sine theta, and that will all be over g. Okay, so if you notice that if we have negative v sine theta minus, we're subtracting these two, so we get a minus 2 v naught sine theta all over g, and we're talking about, and this actually, g will be negative, so we end up getting a negative divided by a negative, so we end up getting a positive time. So we get, which one is this? 2v sine theta over g. That's choice B as well. All right, the next question here is we have an object moving horizontally with a speed v, and it falls off the edge of a vertical cliff and lands at distance d from the base of the cliff. How far from the base of the cliff would the object land if the height was doubled? So we have to actually do two things here. We have to say, like, okay, well, what will happen to the time? And if you look at what we derived on the left-hand side, number 4, you'll see that time is going to increase, but it's not going to increase by a factor of 2. Okay, we're doubling the height of the cliff. That's the delta y, so it's like putting a 2 in front of delta y. And notice that the 2 that I just introduced on the right-hand side of the equation is under the radical. So I'm really changing the time not by 2, but by radical 2. And if the range, then, we're going to fire at the same initial velocity. So I'm going to increase the time by radical 2. And notice now that there's a direct relationship between time and range. So the range will go up by radical 2. So it will be, and okay, there's two answers that are the same. So it could be either C is 2 rad 2, and that's not correct. So it's just radical 2 times D, choice A. All right, number 7 is a baseball is thrown horizontally. Which statement best describes the ball's motion? All right, so what do we know? If the ball is thrown horizontally, we know that its vertical speed, it starts off at rest and is going to increase at a factor of g. So in the vertical, Vy is equal to V naught, which we said is 0, plus At. So as time goes on, Vy goes up. And then in the horizontal, delta x is equal to, not delta x. Since A is 0 in the horizontal, then V is equal to V naught plus At. And A is 0. So the initial velocity and the final velocity in the horizontal is going to be the same. So we're looking for vertical speed increasing and horizontal speed remaining the same. And that's our choice D. All right, number 9 here. Oh, we're going to skip one here. We have to come here. Here's your next, number 8. All right, so based on your answers following, in which the ball of mass m is rolled horizontally off a table of height h and lands a distance d from the edge of the table. What is the initial horizontal velocity? Well, first things first is we need to use the vertical information, which is right here, and a v naught in the vertical to be 0 to find the time. Our fall time is 2 delta y over g. Okay, so if we substitute this in, we have 2 times h over g. And then use that in the horizontal distance. And once again, the acceleration in the horizontal is 0. And I want to figure out V naught. So V naught is equal to delta x over t. So what we have here is delta x is our big D. We have d over radical 2h over g. And I'm assuming, oh, yep, that is a choice. Okay, so that's choice A. You might, in some cases, actually have to do some algebra to rearrange this and make it look like one of the choices. And in this case, we didn't have to do that. And, you know, something that might come to mind is I might have to square everything to get rid of the square root. And then, so I have V naught squared is equal to D squared over 2HG, which is equal to D squared G over 2H. And then to finally take a square root then. And so I wouldn't be surprised if you had something like this as a choice as well. But in this case, we can just use the original term that we had, which is the d over radical 2h over g. All right, the next one, which is actually an IB question, is a boy is throwing a small stone at an angle to the horizontal. Which one is the following sketches best shows the path the stone as it rises and then falls back to earth? Air resistance is negligible, and the acceleration of free fall is constant. Okay, so this is important. Air resistance is negligible, meaning it does not have a factor. So we have to decide, well, first of all, A and B are going to not be correct choices because that shows an influence of air resistance. So now we have to choose between C and D. And if you look carefully, D has a constant radius. In other words, the radius is staying the same. And what we know about a projectile is delta x is equal to v naught t plus 1/2. Actually, I'm sorry. What we know about a projectile, and we derived this equation that delta y is equal to delta x tan theta minus g over 2 times delta x over v naught cosine theta squared. So if we look at this, we have, and I'm going to do this in a different color here, we have delta y as a function of x is a quadratic. Quadratics are parabolas. So that was actually a nice proof that the path that it takes should be parabolic. So choice C. All right, and then the last one here on the multiple choice, number 10, is a ball rolling off the horizontal table with a velocity v. It lands time t later. And then a heavier ball rolls off at the same speed from the same height. So the mass of that ball, notice that mass is not in any of our kinematics equations. And it's not in there because it does not have an influence. Now, you can argue that it would have to take a bigger push to get it going at the same speed, but that's not what's being asked here. What's being asked is that if the ball's heavier and leaving with the same speed and from the same height, how would the two compare? And so it would be the same. Choice A. All right, and then the last question, which is an IB free response, is got an angle. You're firing it. It's got some wall, and you're trying to see what height would it be at the wall. So the first one is actually, the first two really are just doing some trig. So we have an object going at 28 meters per second at 30 degrees. So we're looking for the v naught in the x and the v naught in the y. So the v naught in the x is v naught times cosine of theta, and that works out to be 24.2 meters per second. And then the v naught in the y is equal to v naught times sine of theta. So 28 times sine of 30 is going to be, sine of 30 is a half, so half 28 is 14 meters per second. So those are the two easy ones. The harder one is figuring out the height. Now you can do this in a couple of different ways, but to do this in one step, you can actually use the equation that we derived in class. And plug in your given information, and that would give you a height of 7.1 meters. And I'm going to actually pick up here in a second video. I'm running out of time, the allotted time of 15 minutes. Okay, so stay tuned for the second video. All right, thanks. Bye.